In this video, we want to model one of the most common situations we're going to have in the introductory physics, the contact force model. We're going to model the contact forces between two objects. So let's just say I have my typical block here, and I'm going to push on this block. Let's push on it with a stick. I might have some poorly drawn person attached to the stick, but I'm looking at this contact force right here. I can say there is a contact force on the block by the stick. So you can see I sort of have my type of force, it's my contact force, it's on the block. Block is my object, here the stick. The stick is the agent. It is the object in physical contact, is the agent, it is the thing in physical contact with my object, which is the block. So the first thing I need to do in working with my contact force model is identify the axes parallel and perpendicular to the surface of the object at the point of contact. Well, let's look at that for a second. Okay. So I've already identified the point of contact. That's in my red box. And so the object is my block. And so the surface of that object at the point of contact is right here. And so the axis parallel to that surface is that blue line. So once I identify the axis parallel, I can find the axis perpendicular to the first axis, which would be, in this case, this horizontal blue line. So once I have my axes parallel and perpendicular to the surface of the object at the point in contact, now I want to find the projections of the original force on this axis. So let's draw my axis down here. And if I remember, this is the axis that's sort of parallel. That's my symbol for parallel lines. Here's my symbol for perpendicular. So this is my axis perpendicular. And we say that this force that the stick was, say, pointing off in that direction. And so we want to find the components of this force on these axes parallel. And so we could find this would be the component of the vector on the axis perpendicular. And then I have this. This would be the component of the force that's parallel to the surface of the object. All right. The component, now, the reason we're doing this is now each of these component forces are going to get their own name for type of force, as well as their own model. The component perpendicular, and again, I'm talking about the perpendicular to the surface of the object right there, is called the normal force. And the component parallel is called friction, or the frictional force. So now we've broken our contact force into two types of forces, a normal force and a frictional force. And so let's now I'm going to come up with a model for each of them. All right. So first, let's develop a normal force model. Normal force model. All right. We often give the normal force a label n, and it's a vector. And the magnitude then, which we signify as a capital N without the vector sign, is, well, as we described, it's the component of the contact force perpendicular to the surface. But there isn't a particular formula that we can use for that, so this either has to be given, or we have to find it. We have to solve for it. There's no way, there isn't a mathematical formula that gives us what the magnitude of the normal force is. It is simply the component perpendicular to the surface at the contact point. All right, so that's the magnitude. The direction we can say something more about. The direction, as we said, perpendicular to surface, and it points from agent to object. So the normal force is a pushing force. And so that we can identify the direction. So it's often important to determine exactly where the agent is in contact with the object to be able to determine which direction the agent is pushing the object. Sometimes it's clear, and sometimes it has to be worked out, but the direction is always determined in this way. All right, so that's easy enough. So let's get on to the frictional force model. So the frictional force, we'll call here, give it a force F and a subscript small f for frictional force, is more complicated. And in fact, we're going to divide our friction force model into two situations. We're going to have where the objects are moving relative to each other, and where the objects are at rest. Okay, so let's do the first situation where the objects, meaning the agent object, are moving relative to each other. Relative to each other. All right. So in this case, what is our magnitude and direction? Let's get well, we can get a picture. Okay. So the magnitude of the frictional force, again, as we said before, it's the component of the contact force parallel to the surface of the object. It has some magnitude, F sub f, that is without the vector sign. But we're also going to say in our frictional force model that it's proportional to the normal force of the same contact force. And so that's important because you may have more than one contact forces on a particular object, but each contact force has a frictional force and a normal force. And so the frictional force for each contact force is proportional to the normal force for each contact force. And so if we were to write just for the relationship for the magnitudes here, we would say that the magnitude of the frictional force, F sub f, is equal to some constant times the normal force. And so this constant, I've written Greek mu sub k, and this constant is called the coefficient of kinetic friction. And this coefficient now depends on the surfaces. It can be approximately found for lots of different types of surfaces, but in the end, this is individual for every type of contact force. So what we will have is we'll have a range of objects, and again, this is something that either has to be looked up in a table for a type of sort of typical types of contact interactions, or something that has to be solved for any given problem. Okay, so that's the magnitude of the frictional force and how it relates to the normal force. The direction, as we've already seen, it's parallel to the surface of the object at the contact point, but it is also opposite in direction in direction to the motion of the object relative to the agent. And so this is important. You have to be very clear when dealing with the frictional force which item is the object and which is the agent. And the direction of the frictional force is in the opposite direction of the object as seen by the agent, or relative to the agent. Okay, so let's just do a quick example to illustrate this. So I'm going to have my block. I'm going to push on it with a stick. And so I am in fact accelerating the block in that direction by pushing on it with a stick. So where are the contact forces on this block? And there's a contact force of the stick on the block, and there's a contact force of the ground on the block. Okay. So let's look at each one separately. Since if I look at the contact force of the stick on the block, if it is pushing exactly this direction, then that force is entirely perpendicular to the surface of my object. So therefore, the force of the stick on the block is entirely equal to the normal force of the stick on the block. There isn't a frictional component if the force is pushing entirely normal to the surface. There is only a normal force. And so and the magnitude of that force either has to be known or it has to be solved for if we happen to know the acceleration. But at the moment, we're just trying to identify that force. All right, so what's happening now on the ground? What is the force of the ground on the block? So here's the surface of the block at the point of contact between the ground and the block. That's parallel. And then there's perpendicular. So if we look for the force of the ground on the block, it's going to have two components. It's going to have normal force and a frictional force. Okay, so let's just identify where those are on our figure. Use a different color to distinguish. Okay, so the normal force is going to be perpendicular to the surface, and it's going to point up because it points from the direction of the agent, which is the ground, to the object, which is above it. Now, since the object is moving this way relative to the agent, which is the ground, the frictional force is in the opposite direction of that motion, and so it points to the left. So this is going to be the frictional force, and that's going to be the direction of the normal force. And so, for example, let's say that we knew that the normal force of the ground on the block, the magnitude of it, was 100 newtons. And let's say that we knew the coefficient of kinetic friction between this type of block and the ground was equal to 1/2. Then we could find that the normal force, this is the force of the ground on the block, is in two components. The normal force of the ground on the block, which is equal to 100 newtons, and we need a direction. So let's say we need a coordinate system. If we call this positive x and that's positive y, our normal force is going to be in the positive j hat, positive y direction. The frictional force of friction and of G on B, the ground on the block, is equal then to the coefficient of friction times the normal force, and from my coordinate system it is in the negative x direction. And so, well, this is 1/2, this is 100, so it would be negative 50 newtons in the negative x direction. And so here we have a contact force broken up into the normal component and the frictional component using our friction model. All right, so that's the first example where the agent and object are moving relative to each other. Let's do a example. Now we have to move on to the next section where we're going to look at where the agent and the object are not moving. Agent, object not moving. All right. So in this case, we have a magnitude which again is the component of the contact force parallel to the surface. We're going to say that the frictional force is proportional to the normal force of the same contact force, and so that means it's equal to some number times n, the magnitude of the normal force, where this is the coefficient of static friction. The point here being that this is what distinguishes the two systems, the static friction, because the agent and object are not moving relative to each other, whereas in the previous example they were. One of the problems is that this mu sub s now is not a constant. That depends just upon the surface. It varies. It is a function, in fact, of all the other forces on the problem. And so, for example, just before we move on, we can see what does it mean. And so imagine if you have some sort of object and you're standing here pushing on the object, and you push on it with some small force and it doesn't move. Well, in that case, this coefficient of static friction has some value. Now you push on it with a larger force and it still doesn't move. The coefficient of static friction has in fact changed. So the coefficient of static friction is not a constant. It changes within the system, and it depends on all the other forces of the problem. What we can say about this coefficient is that mu sub s, this coefficient of static friction, has a maximum value that depends just on the physical characteristics of the system, like the kinetic friction has a constant value that depends on the physical characteristics of the system. The static friction has a maximum value. And what does that mean? Well, if we get over here to our person, here if they push even harder and it doesn't move, that means the coefficient of static friction has changed, but then eventually you can push hard enough so that the object starts accelerating. And so it couldn't take on an infinite range of values. There was a maximum value that the coefficient of static friction could attain. And then once a force went, or once it reached that value, and it couldn't change anymore, then the system was no longer static. We lost this condition, and the agent and object start moving relative to each other. All right, and we'll look at an example here of that in a bit. And so that's the magnitude of the static friction force. And now let's look at the direction. The direction of the static frictional force is in the opposite direction of motion opposite the direction of motion, the object would take relative to the agent, and this is important, I'll describe why in a minute, relative to the agent if friction were not present. Okay, this takes a little bit to get one's head around. So in my example up here, when the person was exerting these smaller forces here and here and here, the box was not moving. If static friction were not present, the object would be accelerating that direction. And so that means the frictional force was in the opposite direction of that motion relative to the agent, so the force of friction was in that direction. The box would be accelerating relative to the ground in this direction, and so the force of friction is pointing in the opposite direction to the motion the object would go relative to the agent if the friction were not present. Okay, so let's just do a simple example with some numbers to see how that works out. All right. So I have my block here relative to the ground, and I'm going to push on it with my agent, which is some stick force. Then I'm going to push horizontally so it's normal to the surface of the normal to the surface at the point of contact of the block that's there. And so the other force I have to worry about then is the contact force between the ground and the block. And so it has a normal component that points perpendicular to the surface between the ground and the block, and then a frictional force. And the frictional force is going to, as we said, be pointing this way in this example, opposite to the acceleration the block would go. Okay, so let's say I push on this system with some frictional force that's equal to 1 Newton in the positive x direction. We'll call this positive x, and this positive y. Okay. And we find out from other from other methods that the normal force that the Earth exerts on the block has a magnitude of 5 newtons. Right. Well, if the system is not moving, if the force on the object is 1 newton, then the frictional force on the object is equal to negative 1 newton I hat. And so if I then push a little harder and say 2 newtons I hat, and it still doesn't move, that means the frictional force has changed. So now it is negative 2 newtons. And if now push on it with a force of 10 newtons, and it still doesn't move, my frictional force is now negative 10 newtons. Now my normal force didn't change during any of these. So if my frictional force, which was equal to 1 newton, I'm going to leave off the units now so I don't confuse it with my normal force. See, you can already see that you can run into problems. This is, I use capital N for the normal force, but capital N is also the unit for newtons, and so that can sometimes be confusing. It's important that you never just refer to these as capital N when you think about them. You always want to think about, what does this mean? This is the normal force. What does this mean? This is the unit of newtons. So you don't confuse when you have to use the same letter in working a physics problem. Okay, so this is equal to the coefficient of static friction times the normal force. Well, the normal force we said was 5 newtons, so the coefficient of friction was 1/5 times 5 newtons is equal to 1. But when my frictional force then attained a magnitude of 2 newtons, it's still equal to the coefficient of static friction times the normal, so my coefficient of static friction increased to 2/5. If my frictional force increased to 10 newtons, then my coefficient of static friction went all the way up to 2 to respond to this force. So you can see how the value of the coefficient of static friction changes depending on the other forces in the problem. However, let's change this up just for a minute and say that our coefficient of static friction had a maximum value equal to 1. So it had a maximum value. In that case, then, the frictional force, the maximum frictional force that friction could provide in this case was 1 times the normal force, which is 5, was equal to 5 newtons. And it would have been, let's just do magnitudes this in a moment. 5 newtons, which meant in this case that when we applied the 10 Newton force, the frictional force would have been insufficient to keep the system static, and it would have accelerated then to the off to the right. And so the contact force can be quite complicated, and so it's worth spending some time because it's so important in doing lots of these types of problems. But the key is that the contact force involves the agent and the object in physical contact, and you break them up into a normal and a frictional force, where the normal is perpendicular and the friction is parallel to the surface of the object at the point in contact. And then you have to identify whether the two objects are moving relative to each other or whether they're at rest. And that depends on which frictional force model you use. And then the normal force model is the same in each case. However, in each case, our model is really a verbal representation, and so you have to use this description of the model to translate that into mathematical relationships given each individual example.